It is often said amongst birders that if you see a hawk during the day, you will see an owl at night. Many diurnal raptors have a nocturnal counterpart that fills the same ecological niche, from northern harriers and short-eared owls in prairies, great horned owls and red-tailed hawks in meadows, to barred owls and red-shouldered hawks in forests. We investigated the barred owl-red-shouldered hawk relationship and each species' dependence on the eastern gray squirrel. Barred owls and red-shouldered hawks are opportunistic hunters, meaning they will eat what they can catch. However, a majority of their diets include rodent species, such as the abundant eastern gray squirrel. Barred owls and red-shouldered hawks live in forests, often near sources of water, which ensure that a variety of prey is widely available. Red-shouldered hawks hunt during the day and rest at night. The barred owl will roost during the day, and at night, they are deadly. Examining these counterpart relationships can give us insight into complex ecological interactions, especially in competition. By using differential equations to model two predators competing for the same prey, we can find points of stability between the two raptor species and the eastern gray squirrel. That ultimately gives us insight into the future of the ecosystem and can point us to numbers of each population that give rise to concern about the survival of each species. To model this situation of two predators competing for one prey population, we set up a modified version of the Lotka-Volterra model, which assumes exponential growth of prey without predation and that the environment does not favor one species over the other. Modification was necessary due to accounting for the competition of the two predators. Without modification, the model is less accurate to the real natural system. The first equation represents the prey population. Within it, we describe the growth of the prey populations and the loss of individuals by the success of barred owls and red-shouldered hawks hunting. The second represents the barred owl population. We chose X because owl feet are zygodactyl, 2 toes in the front and 2 toes in the back. The third equation represents the red-shouldered hawk population. Each of the predator equations contain a natural death rate, a growth rate based on the prey population, and a competition term, which takes into account that all individuals will compete within their own species and with the other species. We made assumptions that the squirrel population only decreases as a result of the predators, the squirrel growth rate and raptor death rates are constant, and the barred owls and red-shouldered hawks depend on the exact same resources. We began by establishing biologically relevant parameters through research. Barred owls exhibit an adult death rate of approximately 9% and a hunting success rate near 50%, while red-shouldered hawks have a 24% adult death rate and nearly 79% hunting success. Squirrel growth was estimated around 250% annually, aligning with observed reproduction under favorable conditions. We also estimated that each population grew by 28 thousandths per squirrel consumed. Carrying capacities were set to reflect spatial density data, such as 4 owls and 2 hawks per square mile. We set a carrying capacity of 4 total raptors without the squirrel population present.
We chose to analyze this model numerically. Since there are 3 distinct species and it is a nonlinear system, it would be difficult to draw conclusions with a different analysis method, such as a phase portrait. We first found the trivial solution by setting each equation to 0, and then used Mathematica code to find the non-zero solutions. Since we are looking at change in populations, we can eliminate any negative solutions as they do not make sense in the context of our model. To analyze the system, we created a Jacobian matrix, then found corresponding eigenvalues to each of the equilibrium points. Since these eigenvalues are real, non-zero values, the Hartman-Grobman theorem allows us to classify the system's behavior at these points. From these values, we can see that the system stabilizes at 389 squirrels, 5 owls, and no hawks. We can also see that the system is semi-stable when there are no squirrels and approximately 4 hawks or owls. Using these parameters, we can graph each species population with respect to time. Both of the plots in Figure 1 show the same system, just with different ranges. In the left plot, we can see the owl population increases while the hawk population decreases. We can expect the owl population to grow towards 5 and the hawk population to continue to decrease towards 0. The plot on the right shows a sharp decrease in the squirrel population before it begins to level out and slowly grow. This is expected. As time continues, the squirrel population will increase towards 389, the equilibrium. Of course, the parameters within this model are very specific. Altering them, even slightly, could potentially result in a very different outcome. For example, Figure 2 models the same system as Figure 1, with one exception. The hawk growth rate was increased to 0.03. This is a very small increase, but the model looks very different. In this scenario, the owl and squirrel populations die out, while the hawk population levels out at 3.76 birds. We can also see a drastic change within the populations by changing the squirrel growth rate, which was originally at 2.5, or a 250% increase per year. Figure 3 shows that by decreasing this to a 200% growth rate, we see the squirrel population begin to die off. Both the hawk and squirrel populations approach zero as time increases. Since our model includes some level of alternative resources to support birds, the owl population approaches approximately 4 birds.
First, our model does a good job of capturing the main interaction between two predator species, the barred owl and the red-shouldered hawk, and their shared prey, the eastern gray squirrel. We've used realistic biological rates and carrying capacities to ground our equations in actual data. However, the model also makes several simplifying assumptions. For instance, it tends to predict that either hawks or owls die out completely over time, which isn't really what we observe in nature. Another limitation is that squirrels in our model only die by being eaten, and we didn't include a natural death rate, so their population dynamics aren't fully realistic. We also assume a homogeneous environment, so things like territory, age differences, and seasonal changes aren't reflected. Real populations have spatial variation, age structures, and are influenced by random events like weather or disease, but our equations don't capture that complexity. Another important point is sensitivity. Even small tweaks to our parameters, like increasing the hawk's growth rate, can lead to dramatically different outcomes. For example, just a slight increase in the hawk's growth rate can wipe out both the owl and the squirrel populations entirely, leaving only hawks. Lastly, some of the equilibrium population numbers our model predicts are much higher than what's actually seen in the wild. For example, we might get hundreds of squirrels per square mile, when in reality it shows a much lower number. Despite these limitations, our model does reflect certain ecological principles, such as competitive release, where if one predator declines, then the other can take advantage and increase its numbers. There are several possible improvements that could be made to the model. For one, we could add a natural death rate for the prey, so squirrels don't die only from predation. We could also build in spatial modeling to represent territorial overlap and habitat fragmentation, since not all individuals are evenly spread out. Another big improvement would be to let some of the model's parameters, like growth rates, vary over time to simulate things like seasonal cycles or migration patterns. Introducing random or stochastic elements could account for events like disease outbreaks or harsh weather, which can have huge impacts on real populations. Finally, we could model multiple prey or additional resources, since in nature, predators often switch food sources if one becomes scarce. The goal of these improvements would be to make the model more predictive and reliable for real-world applications, like conservation management, and to bring our simulations closer to the ecological complexity we see in nature. Firstly, we learned that an abundance of prey is absolutely crucial for predator success. If there aren't enough squirrels, both predator populations struggle or even go extinct. Our model also shows that competition between predators can also sometimes suppress both populations, or in other cases, allow one species to thrive if the other declines. One key takeaway is that even small parameter changes can dramatically tip the balance, showing just how sensitive and interconnected these systems are. Even though our model has some flaws, it's still a valuable tool for visualizing, testing hypotheses, and planning real-world studies. It helps us see the big picture and highlights why monitoring both predators and prey are important for maintaining ecosystem stability.